let's start talking about 1D. And in 1D, one of the challenges of this is, we go through step 1, step 2, we solve the problem in S, and then it becomes hard sometimes to get back to the time domain. So the problem that we had, this is not a 1D problem, but what I want to do in preparation for talking about 1D is show you how you go from S domain to time domain when the problem is really complicated. So there is something called Talbot inversion. Talbot, let me write that out. So it's Talbot inversion. So you don't need to know this method other than that it exists and how to use it. And you don't need to know it because I can't figure out how it works. Okay? So there's a Talbot inversion. It's basically a numerical way of inverting from the S domain to the time domain. So let's knowing that we're going to need to do this for 1D, let's take our existing 0D problem. Let's assume we never got past this point. Like we plug this into Maple and it says, sorry, I don't know how to do this. We can't find a way of simplifying it. Let's look at the implementation in Python and I'll show you this Talbot inversion function. Okay, so here's our implementation. Again, we have the analytical solution that we developed here. Talbot inversion is basically a function that you would call from Python. And what you need to do for Talbot inversion is you need to define a function that's going to return the value of TS, right? So your temperature in the S domain. So if you see up at the top of this function, I've defined my own function called Laplace1. To Laplace1, I need to pass several things. I need to pass S. Talbot inversion will manage S for you, but you just need to have your function take it in. So you pass S, and then you pass anything else, any other constants that you need to evaluate your function. So you see there's T infinity, all that other stuff that appears. That's just the representation of T in the S domain. That's where we would have left off. So I just plug that into a function, give that function name here, and then I need to give this function a vector of time that I want to evaluate. Let's see, what are the other arguments? So blanking on what this one is. I'll have to come back to that. T infinity, so then these are all the other arguments that you're passing in. So maybe that is up there, T, yeah. So this might be some like numerical precision setting. We'll come back to that. But these are all the arguments that you're passing in optionally to your function up there. So you just call this, and then when you call it with that vector of time, it's going to give you back the actual temperature in the time domain. So it's kind of this. It's kind of amazing, actually, if you look at it. And we can look at the function itself. Talbot inversion is something that doesn't come with like Python or MATLAB if you're using that. It's a separate function that was developed by somebody at Columbia or somewhere. And what we've done is I have this script in the lecture folder, and if you're using it, you just download the script, put it in the same folder as whatever other file you're calling, and then you can just import it. So the function itself is taking in a number of terms. So that 64 is the number of terms to sum for each T. 64 is recommended. Okay, so we just use the default. Here's the function, right? So this is it. You have some delta, some gamma, and then it's doing a computation to invert it. So that's it. And again, I can't figure it out. It has something to do with imaginary numbers, and it's taking the piecewise two-dimensional summation. But if any of you are good mathematicians and want to figure it out, or read the paper and write a little report for me, that's great. Go ahead, do that. But anyways, it's really cool. So it takes the stuff in the S domain and it flips it to the time domain. So let's prove that it works. We have our function here. We wrote our t hat of s expression here, and then we just run it. And plots here. So yeah, so you see the black line, I guess. What do we do? The black line is the analytical solution. The blue dots are the Talbot inversion points. So it exactly matches. Because it's numerical, there's going to be slight error involved. The more terms that you add on, I think probably the better it does. But it's this really incredible technique that you can use really to get out of a jam when you have too complex of a formulation. The one limitation I will say is that Talbot inversion really struggles at time equals 0. So if you're evaluating a problem, you probably want to evaluate your time not from 0, but from some small time, just after 0. So don't forget that. Like, it'll mess you up and you'll not know what's going on. So make sure you don't start at 0. That's the one limitation. Okay, so that's Talbot inversion. Let's talk now about actual 1D problems. So going through, totally blank page. So this is, I need a title here, Laplace for 1D transient problems. So let's take an example that we'll walk through, and it'll help us understand some of the concepts here. Let's say we have a wall, some plain wall like this. And over here on this side, I'm going to draw this. Over here on this side, you have some material. Make this bigger. This is not going well. Try this again. Okay, so you have some material over here. And off in this direction, it's sort of infinite. Let's see, that's not, I'll just erase this. You know what I'm drawing, right? So you have something, a wall, arrows. Okay, the wall goes that way indefinitely. All right. And over here we have a condition, temperature is a function of time, or T infinity is a function of time. And that temperature is given to us as an expression, which is T initial is equal to, T initial plus beta times time. Okay, so there's a time-dependent ambient temperature function over here. And we want to know what happens to the temperature profile in the wall as a function of time. So we've already kind of been through this before, where you have, you see this wave and it starts to propagate out into the infinite wall. But what we had before was you go from T infinity up to Ts and instantaneously. Now we have a boundary condition in space that's a function of time. And that becomes more complicated, right? It turns out you can solve this with separation of variables. If you wanted to try that, you could. But we'll go through this and get to the point where we have an expression that we can do the Laplace transform on. Okay, so initially we'll say T is equal to T infinity everywhere, right? So the entire body is initially at T infinity. Let's see. So I think what we want to do is let's develop a bit of the conceptual understanding like we usually do. And then once we have that conceptual understanding, we'll know what to expect, and then we'll go through the problem. The first thing would be, you start at some point in time, and what are we going to expect that the temperature profile is going to look like? Well, it's going to, you're going to have some temperature that's sort of growing on the surface with time, and with time you're getting this wave that's propagating over to the right. Right, something like this. So this would be increasing time, T. We can use the same idea of this resistance model to understand what's really governing this problem. In this problem, we have, let's say we have convection over here. So this surface on this side is exposed to convection. And if we wanted to write a resistance network that describes this problem, it would be sort of like the following. So we are at our T infinity, which is a function of time. From that T infinity to the surface, there's going to be a convective resistance. That would be like this. and this would be our surface temperature, which is also a function of time. And then in the body, there's going to be a resistance. And what is that resistance? Obviously, it's conduction, like this. But what is my, say, endpoint temperature on that resistance? Anybody have a guess there? We're conducting from TS here. What's the endpoint temperature in this resistance network? Lucas? Right. Yes, T initial, thank you. T initial, right? Because as you go out in this direction, this is all still, sorry, T infinity, T initial. So the driving temperature difference is always Ts minus T initial. The resistance is growing with time, but it's always anchored by this T initial. It's an infinite wall, right? So this would be our convection. This would be our conduction. Our conduction depends on time. So let's write out just a really simple model for this, and then we'll kind of see what's really driving this problem. So first, our convection is going to be 1 over h bar a s. Our conduction is going to be the thickness or the length of conduction. So the length that it's conducting is equal to that delta t that we talked about. So delta t, the thermal depth of the wave. So that'd be the delta t over k times AC. So delta t is changing with time. This conduction is changing with time. So we have those resistances. Then we write a heat transfer model. So Q dot is equal to T infinity minus T initial. Right? T infinity is a function of time, by the way. Over, these are in series, so it'd be R convection plus R conduction. Let's substitute in our definition of T infinity. So that was T initial minus, plus beta times time minus T initial over R convection plus R conduction. So it turns out the function is actually just beta T over the two resistances. So that's our heat transfer relationship. Write that out all the way. That becomes Q dot is equal to beta T over 1 over h bar a s plus 1, delta T. Let's write it out. So delta T was what? That was the expression square root of alpha T, right? 2 square root of alpha T. So we can actually make that substitution here. We would say 2 square root alpha T, that's our thickness, over K AC. So looking at this, we can maybe immediately understand something about the problem. There's two things happening here in the denominator. One is you have this kind of fixed term. So the heat transfer in the problem is always governed at least by this, but this thing is changing with time. So right away at like t equals 0, this thing becomes 0. And the entire heat transfer is governed only by convection. But as t gets larger and larger, this presumably is going to, at some point, become much larger than this. And now this is going to govern. So you have these kind of two different regimes in which the solution is going to respond. Yeah?
If the t is 0, is the numerator also not 0?
Yes, but like so say shortly after 0.
Oh.
Right. So yeah, at 0, there's no temperature difference.
Yeah.
But shortly after 0, when this term evaluates to something much less than this, right? The point is that you're just going to have these two different governing responses. Okay, so if we know that, I guess we could go to the trouble of, let's see, plotting it out. But let's maybe, we've done this for heat transfer. Let's go through the temperature solution and get something equivalent there. So we have our let's see where to start here so I'm not duplicating too much. You know what? I'm just going to skip this slide. Let's go to the next one here. So we should be on 17.6 if you're following along. So we know that there's these two regimes. I guess what we could do is, what happened here? I have a duplicate. OK. We should be on 17.6. We're all there. So we know that there's two regimes. And what we can do is plot them out. And I'm going to make this so you can actually see it. We're going to plot these out. So I would take my initial response where I know that there's one kind of characteristic. And you could look at that t over square root of t and infer from that the slope of the plot. And then you look at the t over the time over the constant and infer the slope of the plot. And you see that these two kind of characteristic responses exist. So they exist both for the heat transfer rate, and there's a certain expectation that we have here. And then there's another expectation for temperature because the relationships are slightly different, right? But we can go through this, and we know just before doing any real computation that the plot had sort of better look something like this, at least on a log scale. So let's, with that expectation, kind of keep that in our back pocket. Let's move on to the actual derivation and go through the process.